Welcome back to Precalculus. Today we're going to wrap up the final section of Chapter 1, which means, well, it means two things. First, there is going to be a quiz between this lesson and the next one. And second, there's going to be a test on Chapter 1 not long after that. Now, I hope you're feeling well prepared for both of these. The next lesson, not this one, but the next one, will be a chapter review, and hopefully you'll find that beneficial. Now, in the last lesson, we spent a lot of time discussing the alligator data and linear regression, the line of best fit. But toward the end of the lesson, I made the observation that the data in the scatter plot and in the plot of the residuals had a bit of a parabolic look to it. Today, we're going to see that not all models are linear, and that sometimes a quadratic model is superior. Let's see how. Linear regression supplies us with the equation of a line of best fit. So what do you think quadratic regression supplies us with? Well, if you're thinking, well, maybe it's a quadratic equation or a parabola of best fit, you'd be exactly right. And if you're also thinking, I sure hope my TI-84 can do that, because it sounds like it would have to be like awful to have to do that by hand, well, I'm happy to report that yes, your TI-84 can do that. The general process is the same. You enter the data into two lists on your calculator. But instead of selecting linear regression, you instead select quadratic regression, or quad reg, as it says there, and the machine does the rest. You will also note that there is no R value with a quadratic equation because the correlation coefficient R is specific to linear regression. However, there's still an R squared value, and that will prove helpful to us. Now, example 3 asks us to take the American alligator data and to complete a quadratic regression with it. Now, I've already placed the data into the calculator, so I'll show you how that's done momentarily. Basically, we're going to redo what we did last time, but quadratically. First, you'll need to put the data into List 1 and List 2, as I already have. So just as a reminder, go to Stat, Edit, Option 1 there, and you can see that the data for the alligators has already been entered. Let me also remind you about the plot, the scatter plot. If you do second and then the y equals button, it says Stat Plot above that. Make sure that plot 1 is on. Mine already is. And then you hit Graph, and you see there's the scatter plot that the graphing calculator has already made for us. Now, that's all fine and good, but we actually need to get the equation. So let's go back to the Stat menu, go over to the Calc menu, and then notice option number 5 here, Quadratic Regression. Let's hit Enter on that, or you can just press a 5. Notice the X values come from List 1, which they should. The Y values from List 2, which they should. These other two do not need to be dealt with. Then we hit Calculate, and we have the quadratic regression equation. Notice that it's in the form ax squared plus bx plus c, as quadratic equations typically are in standard form, and the a, the b, and the c values are all given there to you. Now, the fact that the r squared value of 0.987 is so close to 1 tells us that the quadratic model does seem to be a very good fit for the data. And since the linear value of r squared was only 0.866 or thereabouts, the quadratic model would appear to be a better model than the linear model. Now, focus on that for a second. There were two models we found. There were two. One of them appears to be better than the other, based on the value of r squared. Now, with the quadratic equation, 98.7% of the variation in weight is explained by the variation in length. And the fact that the residuals graph over on page 62 is a lot more random looking is actually another good sign that the quadratic model is desirable. But just how good is this model? Now, despite that impressive r squared value, it actually has one significant flaw. Notice that, like any parabola that opens upward, it has a minimum value. And it's in the vicinity of x equals 66, right about there. So that means that our model is telling us that as an alligator grows from a baby up to a length of about 66 inches in this part of the graph here, that it's actually losing weight as this happens. So we'll have to conclude that this model is not especially useful for alligators below 66 inches in length. And you might recall that the linear model didn't work very well either for alligators below about that same length. So this again reminds us that interpolation is usually reliable, but extrapolation is not so reliable. And there are other types of models out there besides linear and quadratic that we will learn about in future chapters. And perhaps one of those will be even better than both of these. Okay. So now we're going to set the alligators aside and we're going to look at some new data. Data about what is today the largest city in the United States, the Big Apple, New York City. Now, I'm personally quite fond of New York City. I used to have relatives who lived there, and in fact, I was born in Queens. My parents moved there for a few years after they were first married, and although they moved back to their hometown in Pennsylvania the year after my birth, I still have that New York birth certificate. Now, New York City wasn't always the largest city in the USA. If you look at the data on page 62, its population in 1800 was only about 60,000. But it grew quickly after that, hitting 500,000 by 1850 and 1 million during the 1870s. Now, perhaps you're thinking that we have a lot of large numbers here, and that it would be boring to have to enter all of those big numbers into your calculator. So one thing that we often do, especially with data for years, is to change the numbers into years after a certain date. In this case, we'll change the years data to years after 1800. So that's going to make the 1800 into a 0, the 1810 into 10, and all the way up until the year 1890 becomes 90. With the population data, it's also common to use thousands of population rather than the actual number. So we'll change all the population numbers to thousands of people. So that means that the 1800 population number of 60,515 is rounded to 61 thousands. The next number is rounded to 96 thousands, and all the way up to the 1890 population, which is 1,515 thousands. It is this data that you now see that we're going to put into the calculator. Now, you should recognize pretty quickly that the data in the table does not appear to be linear, because as the decades roll by, the population is increasing faster and faster. It's not a linear sort of change. So we're going to go right to a quadratic model and see what that tells us. The data needs to be entered, and once we hit edit, you'll see that we still have the alligator data in there. So what we're going to do is we're going to enter this, and I hope that you'll do this with me because it is a good exercise for you to do. So I'm going to start here with list 1, and this is the year data. The first year is 0, so 0 and then enter. This column is going to be easy because we count by tens. 20, 30, 40, 50, 60, 70, 80, 90 is the last one. Now we still have more data, so what we're going to do is we're just going to go up to the delete key, and we're just going to keep hitting delete until all of those other numbers are gone. Then we go over to list 2, and this is where we have to enter the population data. The first number is 61, the next one is 96, the next one is 124, and then 203, and we just keep doing this until, again, we have all 10 numbers entered. So 313, 516, 814, 942 after the Civil War, and then 1206, and 15, 1515. And then again, we still have some extra values here, so we'll delete those. And there we go, 10 ordered pairs showing the population data. Now, just to be clear, x should be the independent variable. And with change over time data like this, the time, in this case the years, is going to be the independent variable. The population is the dependent variable, so it is the y. So now let's get to the quadratic model. We're going to go back to the Stat button again, and we're going to go over to the Calc menu, and then we're going to go down to Quadratic Regression, as we did before. We're going to hit Enter. And you see that once again we're asked to make sure that we have the right lists, which we do, and those two remain blank. And then we go to Calculate, hit Enter one last time. And you see that we have the coefficients now to many decimal places, and really rounding the coefficients to the nearest thousandth is probably more than satisfactory for a problem like this one. Now let's get the scatter plot. So we would normally go up here and do second and stat plot, make sure the plot is on, which it still is, and then go to graph. And you'll notice we do not have 10 points on the scatter plot. It only looks like we have 6, and that's because the window needs to be changed. Now in your book, you'll see that they've got a graph of the scatter plot. So we're going to try to mimic what they have there. And we're going to make x min -10, and we're going to make x max 110. And then the x scale, let's just change that to 10 to better match what's in the book. Y min is going to be -200, so -200. And Y max, remember the highest Y value is 1,515, so we're going to have to go higher than that. I'm just going to go to 1,800, I think will be adequate for that one. And then for the Y scale, let's say 200. All right, so with that all in there, we'll go back to the graph, and you see we have our 9, 10 ordered pairs. Good, they're all there. And the next thing that we're going to do is we're going to go back and we're going to also put in the regression equation to see how it compares. Now in your book you can see that we have 0.17, 0.175. I'll use the variable button x squared, and then we have plus 0.579x. You can do 0.579 if you like, and then plus 53.445. So 53.445. And then if we graph that as well, notice almost all of the data points are very, very close to this curve, which indicates that the model is pretty good. The remaining thing we were asked to do was to use the model to predict the population in 1900. Now naturally, you would expect it to be something larger than 1.5 or 1.6 million. So let's see. Now please remember though, that this equation uses values of x that are years after 1800 and gives population numbers that are already in thousands. Now since the calendar year is 1900, x is equal to 100. And when we calculate this, our result is about 1,861,000, which means the population of New York City is predicted by this equation to have been about 1,861,000 people. Now you might be surprised to know that the actual population of New York City in 1900 was about 3,437,000. Now this brings to mind two things. First of all, extrapolation is being used again here, and extrapolation should always be used with great caution. And second, there's actually a vital historical fact here. In 1898, the city of New York, which at that time consisted of Manhattan Island and part of what is today the Bronx, and which was already the most populous city in the United States, it consolidated with Brooklyn, which was the fourth most populous city in the country, and Queens and Staten Island and the remainder of the Bronx. So this new city was roughly double the population of the original city of New York and contained a whole lot more land. Now, interestingly, the population of New York City did not grow steadily in the 20th century. By 1930, the population had doubled again to nearly 7 million, but it did not reach 8 million until about the year 2000. The paragraph at the top of page 63 provides us with another warning. A high coefficient of determination, close to 1, does not imply any sort of cause and effect relationship between the variables. Now, there might be. The independent variable's change might cause a change in the dependent variable, as it was with the alligator data. Or the dependent variable's change might cause a change in the independent variable. Or there might not be any cause and effect relationship at all. Or there might be a third variable that we aren't tracking that is changing both our variables. So avoid jumping to any conclusions like that. Now that we've reached the end of section 1.9, I want you to turn in your textbooks with me back to page 67, where we have a section called Data Analysis. Now you will see these data analysis sections in various places in your book, and while we might not do all of them, we're going to take some time to discuss them as time allows. Now this one is especially interesting because it deals with the topic of baseball. Now I like baseball, and my favorite team, the Bronx Bombers, is historically known for hitting a lot of home runs. And that brings us to the table of data at the top of the page. Now the horizontal distance refers to the distance from home plate, where the ball is hit, to a point on the ground directly beneath the ball. The height is the number of feet the ball is above the ground. So be sure you know what those values represent. When the ball was initially hit, the height was 3.4 feet, meaning the pitcher probably left a big, fat, juicy pitch high over the middle where the batter could crush it. And when the ball was horizontally 100.6 feet away from home plate or near the infielders, its height was about 52.1 feet, which meant those infielders had no chance of catching it. So how far do you think that ball is going to travel before it lands? Well, let's create a model and let's use it to get an estimate. Question number 1 asks us to do a linear regression. So let's enter the data into our calculators, or something else if you're using something else, and let's get some answers. To enter the data, I press Stat and then Edit, and then put the numbers into List 1 and List 2. Now, as you can see, I've already done this. And if you want to pause the video to do it yourself, please do so. Now, to find the data we want, we go back into the Stat button. So I'll push the Stat button, and then the Calc button, so arrow over to that. And then this time we're going to go to option 4, the linear regression. All right, so I hit Enter. And again, we make sure that the data is in lists 1 and 2, which is where we want it, and these are left blank. And then we go down to Calculate, and we press Enter, and we get some results. Now remember that this A value here is the slope of the linear regression equation. It's not notated as m. So the equation is y equals 0.2535x plus 19.2861 for our line of best fit. The r value, our correlation, is about 0.88, which tells us that as one variable, the horizontal distance, increases, the other variable, which is the height, likewise tends to increase. The coefficient of determination, 0.768, tells us that about 77% of the variation in the height is explained by a variation in the horizontal distance. But if you're perceptive, you've already noticed something here. It's a line. And if we extrapolate the horizontal distance, then presumably the farther the horizontal distance, the greater the height, and that simply cannot be because the ball will eventually come back down to earth. Furthermore, we know from experience that the path of a batted ball much more clearly resembles a parabola than a straight line. And therefore, a quadratic regression should probably be done. So back to the calculator we go. The data is already in here, so to get what we need, we press Stat, and then Calc, and this time we go down to Quadratic Regression. All right, and the lists are, again, the ones that we want. So we calculate. And this time we see A, B, and C values. And those are the values that we find in the standard form ax squared plus bx plus c. Our quadratic equation of best fit is going to be y equals negative 0.00155x squared plus 0.71887x minus 0.22256. And we can use it to find the estimated height y at any given horizontal distance x. The r-squared value is an impressively high 0.9855, which tells us that nearly 99% of the variation in height is explained by a variation in horizontal distance. The graph you see here also shows that every data point is very, very close to the parabola. So we can conclude that this quadratic regression equation is indeed a good model for the ball's path. Now that quadratic equation can also be used for other purposes. We can use it to estimate the greatest height because we can find the vertex of the parabola. Negative b over 2a is the formula, and since we know a and b, I will save you the trouble. The maximum height is about 83.2 feet. And you can verify that, of course. You can also predict how far horizontally the ball will travel before it reaches the ground. Since y is the height here, and the ground has a height of 0, we can rewrite the equation to be 0 equals the rest of that. Now, we'll need to use the quadratic formula, but if you do, you'll get two solutions. One of them is the answer, a horizontal distance of about 464 feet. The other solution is approximately 0.31 feet. Now, that's not exactly correct because it's unrealistic. The ball did not hit the ground a few inches in front of where it was struck and then fly for over 400 feet. Remember that the regression equation is actually just an estimate, so it's okay to get answers that are close. These are predictions. These are estimates. We might even call them intelligent, well-informed guesses. But if you're like me, you might be harboring one vitally important and as yet unsaid question. Is it a home run? Is the ball going to clear the fence? All right, well, we know the equation, and let's say that the 10-foot high fence is 381 feet away in that part of the ballpark. Since x is the horizontal distance, we can replace x with 381. And at this point, we become exceedingly grateful for calculators, and yours should tell you that the height y is about 49 feet when the horizontal distance is 381 feet. So it's easily going to clear the 10-foot fence, and it is going to be a home run. Now, if you're a diehard baseball fan and somebody tells you that the ball will travel 464 feet before it hits the ground, you already know it's a home run. Because there's no baseball stadium in the major leagues that has a fence anywhere near that far from home plate. But what if I told you that it wasn't a home run? Or what if I told you that it just barely cleared the top of the fence by mere inches? How could this be? Well, it could be that there are other factors. And the biggest one is air resistance, including wind. And wind can keep a ball from traveling as far as it might otherwise, or it might help the ball to travel even farther. But even in calmness, air resistance will have an effect on the baseball and keep it from traveling in a perfectly parabolic path. Now, another factor is simply the accuracy of our equation. First of all, how accurate were the original data points? The less accurate they are, the less reliable the regression equation. And rounding plays a big part too. Did you notice I used 5 decimal places in each of the coefficients of that regression equation? See, even using just 4 decimal places would have made noticeable differences. There could be other factors as well that could affect the accuracy of the modeling equation, but in truth, such equations are both frequently used and typically reliable for many applications relating to projectiles. Now, as we conclude here, it's worth noting that God has given us humans the ability to use mathematical models in a variety of applications, from engineering to manufacturing to, yes, even baseball. And we should be grateful for these tools because they help us to live out the creation mandate and to serve our fellow man better. Now it's time to wrap up for today. A few tips about the exercise problems. For 17 through 20, you'll need to determine both the linear and quadratic equations of best fit for the data and then choose the one that is a better fit. Notice also that number 21 through number 25 are a set, and they go together. And if you want a little bit more practice, you can sneak over to page 65 and do either of the 2 groups of Dallas population problems. See, if you did all of those, and I'm not going to assign all of them, you would discover some very interesting things about the equations. And once again, we have reached the time for a quiz. And this one is going to cover sections 1.7 through 1.9. It will be similar in style to the first 2, so you shouldn't be surprised by anything you see there. So once again, let me review the order. Do the assignment, get it checked, learn from any mistakes you might make on it, then get ready for the quiz. Take the quiz, get the quiz checked, and after the quiz is checked, learn from any mistakes you might have made, and then proceed to the next lesson, which is the Chapter 1 review lesson. I trust you have all that now. Enjoy the rest of your day and do a great job on the assignment and on the quiz.